Okay, so today we have the pleasure of having Franz Pedit from the University of Massachusetts, who will tell us about minimal Lagrangian surfaces in CP2 of high genus.
All right, thanks for the invite. I was at SMRI from the beginning of June, and I do thank all the people who run that place. It was a fantastic environment to do mathematics, so very happy about that. So, okay, so now let's do mathematics. So at the beginning will be a very slow start with lots of pictures, and then at the end or halfway through, hopefully I will move to CP2, which is of course real four-dimensional, so it's very hard to draw pictures in 4 dimensions, and every picture you draw would be a wrong picture. So there will not be many pictures there, but you get the gist of the thing by looking at pictures in the 3-sphere or R3, so in 3 space essentially. All right, so let me start, because that's the theme of the talk. So there was a quote by Gromov, I don't know where it's in, maybe in his book about partial differential relations, I'm not totally sure. You can read it. Essentially, the gist is that if you understood enough of the algebraic and geometric structure of certain objects, in his case, taming forms, so forms taming geometric structures, then a lot of the complicated PDE theory or hard analysis will become unnecessary. That's sort of the gist of it. And my talk is somehow philosophically very close to that. So, and I try to explain what I mean by that. So let's move on here. So, right. So everybody's perhaps familiar with these words hard and soft, right? Hard analysis is real is analysis. Soft analysis is kind of the apply function analysis. Naive. Hard analysis is you have a PDE and they're nonlinear and you don't know what to do with it. You don't even know existence. So you have to prove, do the usual business. You do think of it as some operator on some initially Hilbert, Sobolev or whatever spaces you are at, or and then you have to prove, of course, do regularity theory at the end. So you prove weak solutions and strong solutions. That requires a lot of a priori estimates. It is complicated, and every PDE more or less has its own theory on. You can't just say, see, my lecture stops occasionally. Pulses, I don't know why it does that, but maybe if somebody walks through the door, it stops. So anyway, so soft would mean just do Cauchy-Riemann equations, right? We all understand those. Del bar, d by dz bar. And that's, of course, significantly simpler than any of these other things. Another ingredient of hard analysis is these nonlinear perturbation arguments or gluing methods, which means you have solutions of simple type and you try to glue them together, but the gluing is, of course, never compatible with your PDE, so you glue some smoothly, say, or continuously, and then you have to prove by perturbation arguments that you can actually perturb this initial configuration to a solution of the actual PDE. Desingularization would be a similar idea, that you start with something very simple, which you know, and then you, which is sort of singular, and hence you can solve it, and then you do desingularization of the things. So a typical example, perhaps for people who are more interested in algebraic geometries, I mean, singular would mean you have sort of a cone point and then you slightly make a handle. So, but that's just algebraically, but in PD theory are similar ideas. And of course, all of this we want to replace by just the elementary implicit function argument. So by that I mean not some complicated Nash-Moser type argument on a Frechet space or whatever people do, but just really implicit function theorem which you would prove to your first-year students. So if the function 2 variables, the derivative with respect to 1 variable is non-zero, you can write it as a graph. And we do that in a Banach space, but that proof, as you probably all know, there's no difference between proving it in n variables or on a Banach space. And then there's something which the analysis side rarely sees even or exploits is infinite dimensional symmetry groups, which will in all these problems I discuss will be present. And then that infinite dimensional symmetry group, of course, gives you a lot of extra tailwind, I think, not headwind. All right, and then what's in between here, see, it's nice to both is gauge theoretic methods. So of course there's a huge part of gauge theory is hard analysis, but gauge theory, of course, since it involves B groups, it's also algebraic in some sense. So it has both sides. So maybe if you make this distinction here, I would say this is really analytical, very strong analytical influence. This is more algebraically influenced. All right. So let me give a few examples of hard methods. So the first, I'm talking here about minimal surfaces. So minimal surfaces are surfaces which minimize the area. So all of you have done the experiment, or maybe not. You take a wire frame, put it in soap solution, out there is beautiful soap film. And in 1970, Lawson constructed compact minimal surfaces in the 3 sphere of any genus. So in R3, there are no compact minimal surfaces because the surface film tries to contract to a point. So it can't happen, right? So you only have, as I said, non-compact surfaces, but in the 3 sphere, the round 3 sphere, it's possible to do this. And the equations are non-linear there in the 3 sphere due to this geometry of the 3 sphere. And he had a nice construction how to make such surfaces. And what you see here is, you see the 3 sphere, that's my 3-dimensional space drawn. This is an equator, the blue, and this is a perpendicular, another equator which doesn't intersect this equator. So 2 equators perpendicular, if you like, on the 3 sphere. Yeah? And then I have here 4 points, 1, 2, 3, and 1 is at infinity because that's also but it's okay, we can always come back. And then on this circle I have 6 points, generally with 2k plus too many points, and the k will make the genus. So once you have done this, you form a quadrilateral here. You see this is a nice quadrilateral. And then you solve the plateau problem, which the first Fields medal was given to Douglas solving the plateau problem in R3, meaning given a simply closed curve in R3, is there a soap film in it? Right? So that was the 1930s. Douglas got the Fields medal for that. So that's hard analysis. And then Lawson adapted these ideas and proved the existence of a soap film in this particular domain. It's quadrilateral here. And it's not my fault, right? So it's unfortunate. Maybe it's just too much data, or I don't know. So, and then you use reflection symmetry, since all these lines are geodesics on the 3 sphere, you can just reflect. And then you build the surface. And I show you what the surface looks like. Looks like that. And that for different genera, you see they form a similar pattern. So you have genus 2, you get 2 handles, 3 handles, 4 handles, 5 handles. And if you would continue with this, you can imagine more and more handles in here. Then eventually this thing will become almost spherical on the top and bottom, and you see 2 spheres intersecting perpendicularly, and that in the infinite genus limit, and that's that. But then it remembers where these handles were, and where these handles are, you have to sort of, you could open them. That's a typical desingularization argument coming from infinity back, right? But this is nice surfaces. They were the first surfaces people understood more or less. So, that I should not do, because now it did something which I shouldn't do. So, okay, so this was one example. The other one came a bit later, 85. There was I hope you don't see this well, because there's a guy blowing a soap bubble. That's a quite famous, I switched slide briefly on it. It's a famous painting, I think French, 19th century. So the question was, can you blow a soap bubble the shape of a torus, genus 1 surface? Of course, the answer is no, it probably couldn't do that. But mathematically, the question was, is there a soap film? Now, what is a soap film? That's a minimal surface, close a volume, and you keep the volume fixed, right? Like a soap bubble. You blow a soap bubble, that means there's a certain amount of air inside, and the pressure of the air and the tension of the soap film are in equilibrium. And that is called a constant mean curvature surface, because the value of that mean curvature is exactly the pressure needed to keep that soap bubble a soap bubble. Right? So the problem then was, there's a long story I'm not going into, that there were two different approaches, and people had the impression there can't be any higher genus surfaces. They all have to be, there's only this, the only soap bubble is the soap bubble, no higher genus one. But then Wente took it up, and he noticed that the equations determining such a soap bubble is the Sinch-Gordon equation, which some people in mathematical physics know very well, that if you put here sine, for instance, instead of Sinch, and take it just as u double dot, it's the pendulum equation. And this is sort of a PDE version of some Sinch pendulum situation. Those who do Lie algebra, they know this is the periodic toda for the A1, for the SL2 loop group, or Kac-Moody Lie algebra. So these equations have many incarnations, and I think classical geometers haven't realized all these connections. But anyway, so he proved there is in fact a doubly periodic solution of this equation. And that was done, of course, also by difficult analysis, that you see, it's a very simple equation, but to prove that there's a smooth doubly periodic solution was huge progress. And that was the beginning of a long story of integrable system theory, which Emma is, of course, also an expert in. And I will go a little bit into that perhaps later, or even in the next slide. I don't know. You should look at the slide. Yeah.
I've seen divers blow water rings.
Water rings, yeah, right. But that's yes, but that's a different issue, because you are in water, first of all, and that has to do with fluid dynamics, right? Or smoke rings.
They wouldn't be CMC tori.
No, they would not be CMC tori. No, they would not be. No, there are no embedded higher genus CMC surfaces. So I show you the picture. That actually was known. If they exist, they have to be not embedded. So this is a torus. I mean, you can look at this a long time. I don't have so much time. I might later on show you a movie if that works, where you see how this is constructed. But this is a torus. It looks like three bubbles which are stuck together, but inside a very rich life, which makes this a true torus. That's an immersed torus. It has self-intersections, of course. Okay, so this is the famous Wente torus, what you see here. So that was, oh, sorry. And then in the 1990s, Capuletas is a big name in this story. He constructed, so once people understood you can make a torus, the question was, can you make genus 2, 3, 4, and so on? He proved the CMC so for any genera. And the way he does it is he constructs an approximate surface. So let's, maybe this picture is fine. This would make a genus 3 surface. This makes a genus 4 surface. So the idea is you draw a graph. The graph has been in some sense balanced, and then you just, where the edges are, you have to wait a little bit. You put model surfaces. These are the famous Delaunay surfaces. I can show you on the next page. Principle. So these Delaunay surfaces, Delaunay, French mathematician, 19th century, he constructs surfaces of revolution. And what you do is you roll a conic section. You roll an ellipse, follow the focal point that traces out a particular curve. Looks a bit like a sine wave, but it isn't described by elliptic function. Or you can roll a hyperbola and trace. Should imagine how the hyperbola rolls. The hyperbola rolls down, and this becomes the asymptote, and then it goes back up again, rolls back and forth. And that's these Delaunay surfaces, which you see over there, and maybe soon here, right? And these surfaces, Capuletas used and sticks them together like a child would. So anyways, the idea clear, you stick in these Delaunay surfaces here, and you have to balance them, because these guys sort of push, these guys pull, and so this has to balance here, and then this is a balanced configuration, but that's not constant in curvature here where you glue exactly at these points. There's sort of a C, and you glue them in, and here's just a smooth gluing, but the constant in curvature surfaces, of course, are real analytic because the elliptic PDE. So it has nothing to do with that. Okay. So anyway, so this is a gluing construction, if you like, and then you do perturbation analysis to prove that near this configuration is actually a constant in curvature one. So yes, so this was the explanation of this. So what are soft methods? Well, it's the bunch of names: Hitchin, Costello, Bobenko, Emma, Carberry, and then in a PhD thesis, they constructed CMC tori in all the space forms by integrable systems. So I only sketch this here, so that what happens is that attached to a constant curvature torus is a genus height Riemann surface, right? And here it is. And this hygenus Riemann surface has a Jacobi variety, which those who don't know what it is, it's a genus G torus. So this is a genus 3 surface, genus G torus. And in that genus G torus, you look for a lattice plane, a two-plane. And that lattice two-plane, by some universal map, produces this surface in R3. And this lattice plane, so this is why it's called integrable system, because this object is really obtained by linear flow in this torus. So there's this high-dimensional torus, we have a two-plane in there, which is a lattice plane. So you can see here, the idea was, if you go this direction, if this is about a third, then you would go 3 times, then you hit again a corner, and here maybe this is up to a half, I don't know. And after 2 times in this direction, you hit the corner, so you have to go 3 times in this direction, twice in the other one, and then you close. Right? Then you get a torus. So this is this theory of integrable systems, if you like. So just to take away from it, you can construct them from these integrable systems where these genus of the spectral curves gives you the complexity of these CMC tori, how complicated they look like. So for example, you can do, these are all constant curvature tori. This wraps around the trefoil knot. This picture is actually the spectral curve. This is the branch diagram. So these red points are branch points. So this branches over the Riemann sphere. These red points are the branch points. So you can, each branch point makes a genus. So this is 1, 2, 3, 4, 5, 6, genus 6. This spectral curve has genus 6. The torus looks rather complicated. This spectral curve has genus 4. Torus looks like that. And here's the conformal type of the torus drawn. So I wanted to show a video here, actually, maybe show movie, it says. Okay, let's try that. Let's see whether this works. This would be a miracle if it worked. Here it is. It's the wrong movie. It's this one I wanted to show. And so you see here, I don't know, maybe, is it light enough, you see? Yeah, I don't need to switch the light off. So what you see is 2 of these parameter lines in the plane, in the Jacobian, you go along in 2 directions, and that sweeps out the torus. So each of them is a linear motion, but in space it looks rather complicated. And then you can move that lattice plane inside that 3-dimensional torus, just parallel translate it around, it stays a lattice plane, and then it does this. There's a huge deformation space in some sense, and the higher the genus is, the more is the deformations, and some deformations look more interesting than others. So maybe I can show you the other one, this one. Let's see whether this does anything. Right, so here you get a higher genus example where you move the lattice plane, and so what you see is that CMC torus starts doing weird things, and also first it's planar, and then it becomes very wiggly, and so on and so on. So this is all you can do with this integrable theory. So I want to advertise this theory. The analyst Vente could never do anything like that. There's no way he proves an existence result of this nonlinear PDE. There's no way he can do deformations like that. That's impossible. He didn't even know there are these hierarchies and so on. So, but once you have all that, you can just, if you have somebody who is good enough in computer programming and can do this, you can make these videos from this integrable theory, because everything is a linear flow. So you can just have linear flows after enough mathematics at least. So this is done by a guy called Dugan Hammock, and all the other graphics are by Nicholas Schmidt. So both of them, Dugan was a PhD student of mine, I don't think he ever got his PhD, but and Schmidt was a postdoc, or actually a co-worker for a long time. So he's now at TU Berlin. So let's go back to my, let's not show more movies because we have to get going here. So no more movie. Okay, another smooth soft method is what's called the DPW method, standing for the authors, Dorfmeister, Pease, myself, and Wu. Jokingly, this is always called the Department of Public Works, right? Because they exist actually in Amherst, where I'm from. There's a big manhole with a cover on it, and it says TPW on it. And so that's actually on there's a book somebody wrote, and he put that on the title, that manhole with TPW. So this constructs all surfaces, at least on the simply connected cover, from meromorphic data. So this is the idea that everything is a del bar or holomorphic or meromorphic Cauchy-Riemann solution. And what you use is the Iwasawa decomposition of the loop group. And for those who know loop groups, they probably know the Iwasawa decomposition of just regular compact Lie groups, but there is also an Iwasawa decomposition on loop groups. So what are loop groups? They're really what it says. So this lambda GC is just all loops. So C star do the complexification of this, say, simple compact Lie group G. This is a loop. And then lambda G is the loop in which are on the unit circle in C star unit in the real group G, and plus then you can extend the loop into 0. So this is a you should think of this as decomposing an SLNC matrix into SUN and upper triangular. So plus is the infinite version of upper triangular. So in some nonlinear, non-abelian Fourier type machine. So that's what we developed then, and with this I will explain a little bit how this is then used. You can make all simply connected CMC surfaces. So this was some progress, because now people thought, okay, these people can do everything and they only need meromorphic data. That's the important thing. So it's this whole nonlinearity is gone when you move to the. Yeah, and then there's a third development, which is more recent, by Lynn Heller, Sebastian Heller is a couple actually, and Tresset and Schmidt. Schmidt is the one who does a lot of these pictures here. Tresset is Frenchman, of course. So they attempted the high genus case. And they used this DPW method, and I will explain it. So this is the Lawson surface again, but now, of course, you see the graphics are much more beautiful. And in fact, this is not a photograph. This is computer graphic, but we actually made that also, printed it out, so that big stands in some museum in Germany, in Tübingen, I think. So Tübingen has it. So this was this Lawson genus 2 surface. But they could do much more. So they could, for instance, give area estimates or asymptotic area expansions in the genus, which is very interesting. So the area of these surfaces here, so this is genus 6 here, is given by this formula, and they know exactly what happens in each coefficient. They are multi-log and zeta function type expressions coming in. So there's some number theory here which nobody understands, but you can get very precise asymptotic estimate. You can compute to any order here. And that's beyond the realm of analysis. So the analysts cannot do, the Lawson could not do things like that. So this is very precise and shows much more structure here using this sort of quote integrable stuff. Right? So by the way, these two rows are the same surfaces. They're just projected from the 3-sphere to R3 from different north poles. Here's another such surface. You know, you can now make lots of them, and they're really beautiful. I mean, look at these here. You can put them on your table or coffee table. Wonderful objects. So these are all these minimal surfaces. These are all genus 2, as you can see. There's probably the same surface, just different view in the 3-sphere. So they live in R3. You show them in R3, but they live really in S3. So when you look at them in R3, you have choices where you put North Pole and so on. Okay. So all these examples I've shown you, the structure group is SU2 because you map into the 3-space. The 3-space is R3 or S3 itself is the Lie group SU2, for instance. Hyperbolic space also has to do with SL2C, and real R3 is, of course, the algebra of SU2. So you have always these rank, what is it? The vector bundle has rank 2, and the group is whatever, these groups have rank 1. But then there's interesting geometry in higher rank. So SL3R, that I talked about this in the matrix meeting, and SU3 gives these minimal Lagrangian surfaces. So I want to discuss a little bit today. So let me explain why these are important. Right? So if you do this Strominger-Yau-Saslov mirror symmetry proposal, this goes probably back now almost 20 years. The idea is that you have 3-dimensional Calabi-Yaus which are mirror paired. But the way to construct the mirror has to do with certain Taurus vibrations. So each Calabi-Yau is supposedly fibered by Lagrangian, special Lagrangian tori. So Lagrangian means that the Calabi-Yau is a Kähler manifold, so it has 2 form. So it's a symplectic form, it's a Taylor form, it's a symplectic form, and these have to be, the symplectic form vanishes on this Taurus on the tori of the vibration. So it's Lagrangian and special Lagrangian means that they are minimal but no more. They're calibrated by the volume, by the holomorphic volume form. Just for those who are experts here. That's not so important. You imagine this three-dimensional Calabi-Yau fibered by 3 tori. So these pictures are 3 tori, but they have to collapse somewhere. So they have to degenerate. And so you have indicated here the cross section is a 2 torus, the whole thing is a 3 torus. And if for instance this generators collapses, then you have this picture where these cross sections are 2 tori. So you get a cone over 2 torus, right? So the singularity could be in the simplest case modeled by a cone in C. So the Calabi-Yau 3 manifold becomes a C3. Complex C3, and that cone is. So it's a cone over 2 torus. I've drawn it here. So here's the cone over the 2. There's the cone over the 2 torus in C3. Then I intersect this with the 5 sphere. That gives me a nice torus in the 5 sphere. Now a real 2 torus in the 5 sphere. That is minimal Lagrangian, whatever that means. But then I can project with the Hopf projection S5 down to CP2, and that gives me a minimal Lagrangian guy. So that's why these minimal Lagrangian tori are very important, because they serve as models for singularities in these Calabi-Yau torus vibrations. So the Miller symmetry conjecture says roughly if you have this torus vibration, just dualize the tori, and then you do something more clever where the tori collapse, and that gives you the mirror. That's the conjecture, which is not solved, of course. And so on. But it's the idea. So what you want to do is produce examples. And this has been done. So all of these tori have been constructed in the same way as the constant mean curvature tori, where it's this integrable system. So spectral curve, high-dimensional torus, plane, and so on. So in this, somehow Emma has done work on that also. And higher genus examples are very few, actually. The only ones are Capuletas and Haskins, again, in 2007, and they construct examples in all odd genus. And again, it's gluing theory. So the idea is you start with, well, they do it on the Lagrangian level in S5 rather than CP2, but it's equivalent. So you start with a sphere, which is, of course, a minimal Lagrangian, and then you attach again rotationally symmetric minimal Lagrangians. They look like the Delaunay surface. It's really modeled on that. So the same idea, you stick them onto the sphere, but since you are now in S3, you can get these rotational tori. They're not just cylinders, but tori. And so this is torus, you glue on. Here's another such torus, you glue on. Here's a torus, you glue on. And you can imagine what it looks like. So it's a sphere, and then these tori glued on, and the tori are minimal Lagrangian. But here, where you glue to the sphere, of course, is the best smooth gluing, but that isn't minimal Lagrangian, because minimality again is these objects are real analytic, and minimality means error minimizing, and Lagrangian means that the Taylor form of CP2 vanishes. So these conditions are not preserved in any way by this gluing. So you have to work really hard, again, nonlinear PDE analysis, perturbation theory, to make sure that nearby such a configuration is an actual minimal Lagrangian guy. That's what they did. So it's a very long paper, very complicated paper to get that. So this would be a genus 3 example. So also what you notice here, perhaps, or what one should find out for later, if I ever get to it, if you compute the area of the resulting surfaces, they grow linearly in the genus, because every time you glue on this piece of the torus, so the torus is, you take a torus and cut it a bit away, so that you can glue it here, so make open it. So each time you glue on the same torus here, so it grows in the genus. Every torus you glue on has a certain area, and if the genus goes up, the area grows as linear in genus. So we also do. We have our own way to do this. Our theorem is there exist minimal Lagrangian surfaces of genus k-1, k-2 over 2 for all sufficiently large k. Now, you might say, that's bad, k could be astronomically large, k0. Yes, it is, but that is due to a usage of a very primitive implicit function argument. But in the meantime, Tracey has shown that you can actually get that. If you analyze how the proof of the implicit function theorem works, you can get k0 down to a number like 3 or 4. 0.5, forget somewhere, but really down. So it's not astronomically large. So this genus, and then the moment anybody looks at this genus formula, they know that this is that the Fermat curve, of course, has that genus. So indeed, the surfaces we make, that their conformal type or the Riemann surface type is that of the Fermat curve. And we can compute the area also. But you see, the area grows linearly in K, but K is the square root of the genus. So our area growth is better than the Capuletas area. Capuletas area growth is in genus, linear in genus, ours is linear in the square root of the genus. So this is better. And anyway, so it's just, that's the theorem. Should I stop or do I have more time? Ah, 20 minutes, good. So I want to explain how to, not how to prove this, but the ideas which go into that. So there will be perhaps less pictures now, but it shouldn't be too technical either. So is this mostly came across what's happening here. So in some sense, this theorem was, the idea was people understood, or we understood how to make these Lawson surfaces in the 3-sphere. They had certain symmetries, which I should have perhaps mentioned to you. If you remember, the Lawson surface was this almost a peanut-shaped thing, the holes in it that had a rotational symmetry, and then it had an exchange from top to bottom symmetry. And these symmetries, when you mod out by them, the Lawson surface has a G+1 fold cover to CP1. So that Lawson surface is actually a branch G+1 cover over the Riemann sphere, right? So that's and there, you know, where the branch points are and everything. So that's good information, because the idea then is, well, maybe you can do work on the Riemann sphere where you remove points, branch values are, and then pull everything up. So the problem is significantly simpler by modding out all these symmetries. And that idea we had here, so that's our approach. So we want to make these surfaces, and you can see here, since they have this particular conformal type or Riemann surface type, this is a highly symmetric surface. So we didn't know that initially. We constructed from other principles, but then I think we got this genus formula, and then I said, look, this must be the Fermat curve, and then we proved it was the Fermat curve. So anyway,
I have a question about the previous construction. So how is it clear there that you can get arbitrary large genus? Because somehow here you have your sphere, you have to take out disks. And so
yeah. So here, you mean this one?
Yeah.
Yes.
Make them as small as possible, right?
Yeah, you make them smaller. Yeah, that's fine. I mean, you see, scaling is always no problem in this theory. I mean, you can scale. This can be very small. You see, okay, so these surfaces here, gluon, these Delaunay type surfaces, they call this the neck here, right? The neck can be arbitrarily small. You can make them very thin-necked. You can make them fat-necked, thin-necked. And in the limit, of course, the neck becomes a point. And then what you see is just like what you call it, a necklace of pearls, right, together. But the neck can be arbitrarily small. So that means you can have arbitrarily many disks cut out in symmetric order. So they are typical disks, say, and you make them very, very epsilon small, and then you make.
Then also the perturbation needs to be tiny.
Yeah, exactly. So that's a very good remark. So what you actually get here, if you think of the modular space of all these surfaces, then you get something at the boundary of the modular space, where well, A is highly symmetric, so it's not the generic surface, highly symmetric, and even in the symmetric constraint under all symmetric surfaces on the boundary of the modular space, because you have this necks very, very tiny, because you do this perturbation. And tiny necks. Does this answer this? Yeah. Somewhat good. All right.
Just a silly question. What happens with algebraic subwritings in CP2? How do they?
Oh, algebraic. So if you have so for instance, this sits in CP2, and that is not a Lagrangian surface, but it's minimal. Every holomorphic surface in CP2 is a minimal surface. It actually minimizes the area in its homotopy class. It's the smallest possible area in the homotopy class. So the homotopy class of the Fermat curve in CP2, this is the smallest area it can have.
But somehow the ones you're constructing sit in a kind of fundamentally different way.
They sit very different because they are not holomorphic, first of all, maps, and because Lagrangian condition destroys holomorphism immediately. So not holomorphic. Actually, Lagrangian is exactly the opposite of holomorphic. Holomorphic means the tension space is invariant under V. complex structure on CP2, whereas Lagrangian means that the tension space of this real two-dimensional tension space gets moved perpendicularly. That's equivalent to Lagrangian. So it's some people call it totally real, for instance, totally different. So yes, so these are different. Yeah? They're harder to get. I mean, these are, of course, you know essentially the algebraic geometers can write down, give me a Riemann surface. Well, what's the statement actually in CP2? I'm not quite sure. In the plane, you need singularities. CP3 you could do them smoothly, but in CP2 you can't, because the secant variety has these double points, right? So in CP2, but still, I mean, if you allow some mild singularities, you can do everything in CP2 holomorphically. Algebraic, yes.
Sorry. Are you saying though that these minimal Lagrangian surfaces have a complex structure?
No, they do. No, of course, the surface has a complex structure, obviously. Yeah?
Oh.
I mean, CP2 is not just a holomorphic manifold or a complex manifold; it's a Kähler manifold. So it's as the Fubini-Studi metric.
Oh.
So that metric gets induced on the surface, and that gives you a conformal class, for instance, and that's the complex structure. It's one way. So all the surfaces are Riemann surfaces by construction. Every surface I put in front of you even here in 3 space, is a Riemann surface. Because there's a complex structure, namely take a tangent vector and then rotate that vector by 90 degrees, which you can do in you see what I mean? Is then rotate 90 degrees. That's an almost complex structure, but in dimension 2 area almost complex 30 degrees. So it's a Riemann surface. So that's easy to get rid. Yes, but these are holomorphic. There's a difference. This is also a Riemann surface, but it's holomorphically mapped into CP2. Whereas these minimal Lagrangians, they're not holomorphically mapped into CP2. They're real analytically mapped, but not holomorphically. Your question answered? Yes, good. Let's move on. So, just to give you a slight overview. So this is something to internalize here. So this is where the gauge theory aspect comes in. So you could say, oh, what are the equations for this minimal Lagrangians, for this constant curvature minimal, whatever you do? What are the equations? So the equations, at the end of the day, are encoded in a flat family of flat connections. So you have, in our case, so generally with the theory, you have a rank CR bundle, degree 0 complex vector bundle over the Riemann surface M, and you have a C star means C without 0 family of flat connections. So there's a background connection, and then you have these objects here, tensors if you like, where you have a family. So imagine you have this loop, we call it a loop of connections, and this loop has to have certain properties. For instance, it needs to be unitary if the connections need to be unitary connections if lambda is on the unit circle for unitary lambda. And this phi, which is generally called the Higgs field, is a 1-0 form, and then the flatness of this loop is equivalent to these equations. And these are called signed self-duality equations on the Riemann surface, because Hitchin wrote a paper on the self-duality equation on the Riemann surface where the sign is minus here, but this is a plus sign, so it's signed, interestingly, self-duality equation. And for surface geometers, they look like Gauss equations. You ever heard the name of that? Or Godazzi equations. You learned that in very basic differential geometry. But this is what these equations resemble. So the first equation is a nonlinear equation. It couples this is the curvature of this connection nabla. Is coupled to the square of the Higgs field. This means Hermitian conjugate. What's it called? Hermitian transpose, right? Because there's a Hermitian vector bundle, so this is Hermitian transpose. And this is just the holomorphicity of that Higgs field. And phi has to be very special depending on the problem at hand. Right? So in some sense, what you choose for phi and what exactly that nabla is on this bundle here, that determines at the end what you study. Do you study, constant mean curvature? If R is 2, then you study constant mean curvature surfaces or minimal surfaces. If R is 3, then we do what I want to talk in this lecture here. So
I've got no idea where this is starting from. So are you saying you want to describe the normal bundle for this CMC surface or something like that?
Where these things come from? I mean, where this comes from? What's the question? Where these connections come from? Is that what you ask, or the fees come from?
Like somehow I don't see at all how.
No, you can't see this. Not supposed that you see. I mean, I'm not explaining why this is enough to study this.
But how do you, like, imagine that one has something like this, how do you produce
The
some-
surface?
Yeah.
Yeah, that's pretty, okay, that's a good question. How do you produce the surface? So for that, you have to know that in all of these examples, the phi essentially encodes what people would classically call the second fundamental form, if that means something to you. For certain R3, there's something called the second or Weingarten. And this encodes in some sense the Levi-Jupyter connection or things like that. So that means if you have this object, then you have all the data to make a surface. And conversely, if a surface, you can grind out these objects, and there's an equivalence between those. So in some sense, yes, you can say it's the normal bundle or normal map, Gauss map makes the derivative of the Gauss map is this, for instance, and so on and so on. So I don't want to get into this because we spend too much time in kind of explaining basic surface theory. But the important thing is this is the object you really need, this loop of connections. And they have the flatness is these beautiful equations here, which are in fact, that's why I labeled them Gauss-Bodazzi. These are the integrability equations for a surface. I will make it a little bit more explicit perhaps in the next slide. So if you do the special case of minimal Lagrangians, which I'm interested in, so I said again, Lagrangian means the Kähler form vanishes along M, and minimal means critical for area. The bundle is now a rank 3 bundle, and the Higgs field looks very simple. And the only ingredient in the Higgs field which is not trivial is a cubic holomorphic differential, which comes in for these minimal Lagrangians. They see a cubic holomorphic differential. So that's just what it is. And then you grind out this flatness, and you see this wonderful equation down there. It's called the Zeitzecker equation. If you look at this looks a lot like the Sinch-Gordon equation, just much more complicated. And in fact, it's the SL3 periodic total, which means it comes from the affine SL3 group. So you can do that for SLN, of course. In fact, any simple Lie group has an affine group to it, I mean a loop group to it, and then you can grind out the corresponding equations. They're called total field equations. And this is a certain deduction of the SL3 total equations. So this is what you have to solve. So what's given is the Q. So you give yourself this, say, or you leave Q free and say, well, what are my solutions for pairs U and Q? And U will be a globally defined function on their compact surface N. So the solution of this equation. G naught is some hyperbolic background metric because we want M to have higher genus, so this could be chosen with the metric of curvature -1, so this would be -1. And then you have to solve this highly nonlinear equation. So this is what you would need to do, like Vente did. Vente proved that the doubly periodic solution of Sinch-Gordon. You can now say, can I prove something on a genus 7 surface, solutions of this guy? Nobody knows how to do that, obviously. That's why we don't do it like that. Oh, his time is almost over, yeah, right. Anyway, how much time do I left? No, when am I over? 8 minutes? No, 5 minutes? 3 minutes?
Yeah, 3.
3, that's very fast. Okay, so maybe the gist here is the following. The important is to make these families. A flat connection has a monodromy representation. So you get a loop of representations, the loop group. And the important thing is this representation needs to be unitary along the unit circle in lambda. And that's a difficult problem. So let me just say in genus 0, of course, not a difficult problem because there is no fundamental group. All representations are trivial and you're essentially done. In genus 1, all representations split because it's an abelian fundamental group, and that's where you can have, it has direct sum of 3 representations, and sort of this is a picture, and that's the spectral curve. That's why this integrable system works so beautifully in genus 1. In higher genus, you can't do that, but there's the DPW machine, which tells you there is a way to do it, namely that you can use this huge symmetry group as a gauge group, and then you can gauge this family into a meromorphic family. So this is now a meromorphic connection. And so you have better chances. So it's no longer just a smooth connection, it's gauge equivalent to a meromorphic connection. And once you are there, so maybe I should then go a little bit. Once you are there, you sort of reverse that. The strategy is you start with some meromorphic connection, and then you want to find conditions that you can unitarize it. And that's sort of the difficult thing. On high genus, that's hardly impossible. So we induce symmetries on the surface. you go down to CP1 with 3 punctures, and there, of course, you have a good machine to unitarize representation on a triply punctured sphere. That's what we do here. We write down Fuchsian or logarithmic connections on the triply punctured sphere with an additional parameter, and we make it such that at t equals 0, we know where we are. We have an RP2 in CP2, which is where the connection is unitarizable, and then we try to use implicit function argument to move away from that configuration. And in order to do this, the only thing you need to know is you need to understand the representation variety of the triply punctured sphere. And that has been done, so one has explicit formulas for that. Let me just swipe here. The trace coordinates, so these are the monodromies or the representations around the loops 0 and 1. And these are 3 trace coordinates, and in fact, the representation variety is given by this cubic, affine cubic, and the unitary part is given by a simple x is y bar condition. And that's it, and then you are essentially done. You put all this together, you write out this Fuchsian guy, you use implicit function theorem because you now know explicitly what the unitary part in the representation variety is. You can use implicit function theorem to move away from the t equals 0 part, and you get then for small t, you get solutions which are unitarizable. Then you put t 1 over k for k is an integer, it has to be large because t is small, and then by the construction of this covering, this gives you then the correct, gives you then a genus k minus 1 minus 2 surface. It gives you this connection which is now unitarizable. Then BBW tells you you can go back and find one which looks exactly like U1, and you have your surface. So that's the end of the story. So it's really not that hard if you put this all in. So this will be quick at the end. Sorry about that, but I think that's the gist of it. The gist really is use enough of the symmetry, use enough of your infinite dimensional gauge group, and put this all together correctly, and then at the end you prove, you can get examples of these surfaces without ever having to talk about nonlinear PDEs and complicated estimates and anything like that. And you get more information out of that, area estimates and so on. So now I stop.
Let's thank the speaker.
Yeah.